talk for the day's third talk, defeating TLS client authentication using fault attacks. Our speakers, Nicolas and Sylvain, both are security researchers at Podolsky. And Nicolas, Sylvain, you are live now.
So, hello everyone, thanks for joining. Today we are going to show you how we used fault attacks to defeat TLS client authentication on some devices. But first of all, I will just introduce myself and Sylvain will introduce himself just afterwards. So my name is Nicolas Oberli. I'm from Switzerland. I'm working in the R&D department at Podolsky Security. I mostly do embedded systems security research, so that mostly involves reverse engineering, protocols, firmwares, discovering how devices works, and this kind of stuff.
So I'm Sylvain. I'm working at Nagra IoT security. So I'm mainly doing hardware attack, which involve voltage glitch, EM glitch, and sometimes lasers. So today we will speak about clouds and IoT. So sorry about that. But we figure out that in more and more use cases, we have an embedded device which communicates with a cloud. And usually this device authenticates itself to guarantee data origin, because you don't want that any rogue device would be able to send data to your cloud. And you want to guarantee the authenticity of your data. However, usually these devices are low cost and they have no physical security or very low physical security, which means that we should be able to apply standard hardware attacks. So just before going to the attack, Nicolas will present you TLS in a nutshell.
So basically, when you have a cloud connection, you'd like, so you usually want to have your communication encrypted, which is mostly the case in all of the major cloud providers for IoT. What they usually use is TLS 1.2. So TLS stands for Transport Layer Security. This is something that replaced the SSL, the Secure Socket Layers. It's now nearly used everywhere for HTTPS, for all socket encryption. Its current version is TLS 1.3. It was released in 2018, but TLS 1.2 is still massively used. As a reference, Netflix announced several weeks ago that they switched to TLS 1.3, and this was just a few weeks ago. So again, this is something that is rolled out pretty slowly. And TLS 1.2 is still mostly used for all communications, especially in IoT. So as an example, if you take the Amazon Web Services for IoT devices, you get lots of information on how to set up your new devices to connect with their cloud. And how it works is when you register for an AWS IoT account, you can include new devices to access your cloud or your backends. And this is done by creating a new device and a pair of public and private keys that will be used afterwards by your device to authenticate with the cloud. So Amazon provides a lot of boilerplate code that you can use. They have a basic image which uses free RTOS, and this image uses mbedTLS. And if you get this basic example, you are able to connect to the cloud and make a LED blink on your device. So we got some interest on that. We had a look at which kind of encryptions Amazon provides to connect to their clouds. And amongst the cipher suits that were that are available, there are two of them that are recommended. And the main difference is that one uses ECDSA for the client certificate, and the second one uses RSA. So you can choose one or the other. Then once you register a new device that you want to use, Amazon will either provide you or you have to generate a private and public key. And this private key is, you have to store it directly within your device firmware. So within the code, you write your ECDSA private key, and this will be then used by mbedTLS to authenticate directly to the cloud. And what happens behind the hood? So you have your clients that will try to contact, if we skip our example, the Amazon Web servers. So they will start a TCP connection. The server will then send the basic TLS packets. The first one is the server hello, the server certificate, so it's public key. Then it would start a handshake to derivate the encryption key. And what is important and what is the difference between an HTTPS connection and this kind of connection is that the server will require a certificate from the client with that certificate request. The client will then send its certificate, so its public key, respond to the handshake, and send what is called a certificate verify, where basically it hashes all the previous communication and signs it with its private key. If you can sniff this data, you can see every bit of communication because this part is still not encrypted. And we can see that the last part contains the certificate verify and the signature coming from the device. We can also see the signature algorithm here, which is ECDSA with that specific curve, and the hashing algorithm is SHA-256. So before we go a bit further, we'll just take a look at how elliptic curves work. Sylvain?
Yes. So as Nicolas explained before, TLS allows using RSA or ECDSA. However, ECDSA, which works on elliptic curve, has the main advantage to have smaller keys for the same length, the smaller key for the same security level, meaning that if you have a 4K RSA key, it will be like 256 bit for ECDSA. And ECDSA is a bit better for performance as well. So it's really a perfect signature algorithm for IoT because we have very constrained device. So now let's look at ECDSA. So from this device private key, the signature is computed like with these formulas. So we first generate a nonce k. We multiply k by p, the point on the elliptic curve which was chosen. And then the x component of the result will be the first part of the signature. And the second part of the signature is computed by multiplying the inverse of k times h plus rd, where h is a hash of the message we want to sign. So the output signature is simply R and S. However, there is a strong requirement for this signature algorithm. This requirement is that the nonce must be generated randomly and must be unique for each message sign. And this is really important because from R, the first part of the signature, it's not possible to recover the nonce. It's linked to the discrete logarithm problem, which is believed to be difficult to solve according to cryptographers. However, if someone does not respect the security requirement, if a message, two different messages are signed with the same nonce, then it's possible with a simple formula to recover the nonce. And from the nonce, as soon as the nonce is known, it's possible to recover the private key of the device, which is dramatic for the security. For example, in 2010, a team figured out that all the PlayStation 3 games were signed with the same nonce. So from two different games, it was possible to recover the private key of Sony, and then it was possible to sign code or game, which will be seen as genuine by the PlayStation 3. And yesterday, if you follow the presentation of TPM.fail, you've seen side channel against ECDSA. So now we'll speak about fault attack. And for fault attack, it's quite simple. We can apply the same principle I explained before. If we are able to reduce the entropy of the generated nonce, or we can fix the nonce to a non-value, then we are able to recover the private key D. Because as you can see, we know the nonce, or we can brute force the nonce K. We know S, which is the second part of the signature, which is in clear on the network. We know at H, which is the hash of all the previous handshake, which was exchanged during the TLS handshake. And we know R, which is the first part of the signature. So that's the idea of a fault attack. Now, let's see in mbedTLS how it works and how it is implemented. So mbedTLS is really used in a lot of embedded SDKs. It really targets the embedded world. And as it is stated on the website, it offers a SSL library with intuitive API and readable source code, which is in fact true. And it was really easy to spot where things happen. So we went into the code. We figure out that the nonce is generated in the ECP gen pref key function in the ecp.c file. And this function will call MPI fill random function, which will then call the hardware number generator or software random number generator, depending the target you have. And afterward, it will call a function called MPI read binary. And this function will simply convert the generated buffer to an internal structure. And at the end of this function, we have a loop which copies the buffer byte per byte into the structure. So to sum up, we have a buffer which is converted to an MPI value, and the copy is done byte per byte to the word, meaning that if we are able to stop the loop earlier, after 1, 2, or 3 steps, we'll have a nonce which is non-zero, but which have a reduced entropy. So we can still get back to our idea of attack. We can first generate a lookup table for small nonces multiplied by the generator. So we'll have a lookup table with K and K times P, so that the first value will be the nonce value directly, and then it will be the nonce times the generator. Then we'll have to generate a fault to exit the buffer copy earlier and to have a small nonce. And if we are lucky, we'll have a nonce which will be truncated with a reduced entropy. And if we are lucky enough, it will be less than 32 bits. Then we can make a lookup to our table. And if we find that the first part of the signature is in our database, we've win, because we have directly the nonce, which is the first record in our database, and then we can recover the private key. And during our code review, we also figure out that everywhere in mbedTLS, the return value is left uninitialized at the beginning of each function. So the compiler initializes the value to 0, and at the end, the function returns 0 if it was successful. And it was really nice for us, because when you do fault attack, sometimes you skip large part of code, you are not that precise. But if you have a function which returns the uninitialized state and which will be seen as successful, it's really nice, because then you don't need to worry about error detection. So that was something which helped a bit the fault attack. So now I presented the attack idea. I will let Nicolas explain how we exploit this attack in practice.
So once we knew we were able to maybe succeed in generating faults, we needed a correct target. So after looking at different chips, we came back to the ESP32, which is a SoC widely deployed and available. It's supported by AWS IoT as well. And it has a good advantage that it has an integrated Wi-Fi. So it will be even easier for us to connect to a remote server to test our attack. And it has been proven to be vulnerable to voltage glitching, which is also a nice feature. So there were previous fault attacks on this chip made by somebody called Limited Results. He used voltage glitching and was able to get different achievements with this. For instance, bypassing the flash encryption, bypassing the secure boot, and even extracting the flash and the encryption keys directly from the device. So now that we have our target, first thing first is we have to know exactly how it works. So we dug into the data sheets. And the interesting part for us is to find which pins we need to trigger to inject the glitch. So from the power domains information on the datasheet, we see that our CPU domain is right here. It's powered by a voltage regulator, which is just a bit above. And this voltage regulator is directly connected to those two pins on the chip, so VDD 3.3 RTC and CPU. So once we know that, we take our module, take the schematics for it, and trace both pins to their corresponding place on the PCB. And we can see that they have two bypass capacitors there, which we need to remove in order to make our glitch more likely to succeed. So directly on the PCB, we can see that this is one of the pins we have to take care about. And on the upper side, there's the capacitor that we have to remove. So once we removed it, we also needed to cut the trace from the main voltage supply. So on the back of the chip, we used a Dremel to dig just a bit and cut the trace connecting the main power supply to the pin. And once we did that, our pin is completely free, so we can connect it to another kind of device. So to perform those voltage glitchings, we used a Chipwhisperer, which uses what is called the crowbar method. So it uses a MOSFET that will short the power supply to the ground. So that will cut the power from the CPU, from the power supply to the device under target. So we have here our external power supply that is connected to our Chipwhisperer. The Chipwhisperer from the inside got this MOSFET, and the output of the Chipwhisperer is directly connected to both pins of the ESP32. And with that, we are able to get our setup done. So this is how it looks in practice. So you can see the two pogo pins connected to both the power supply on the chip. And you don't see that on the picture, but behind that, there's the Chipwhisperer as well. Once we set everything up, we also added some small resistors just after the power supply, so we can measure the current consumption of the chip. And what we did as well is within the mbedTLS library, we added a GPIO pin that will go up when the ECDSA computation starts and will go down once it's done. We just did that for to speed up the whole process. But as you can see on the blue line on the graph, you can clearly see the power consumption of the device, and you could be able to do exactly the same with just the power trace to know exactly when to glitch. So this is the glitch shape we have once successful. So it's about 100 nanoseconds width. And with that, we were able to start connecting to a remote server. So we just created an HTTPS server, which requires a certificate. And the firmware that we placed within the ESP32 basically just connects to the Wi-Fi, try to connect using a certificate authentication to our server. And we monitored the computation, the glitch, and the packets that were sent by the device. In parallel of this, we generated our lookup table. So we generated the table for all values of k, so the nonce value, between 1 and 2 to the power of 32. So all values on 32 bits were generated in a table. The final table took, I think it was about 2 days to generate, and it weighs 300 gigabytes. Once this lookup table was done, looking for a specific value within that table took about 5 seconds. This is mostly the same kind of attack that has already been done on Bitcoin. If you want more information, there's a link there. And with that, we started our glitching campaign. So every test takes a bit of time, and after some time, we're able to get the private key directly from the device. So again, to sum that up, we just sniff the signature coming in clear text on the Wi-Fi, take that value, put it in our database, and we are able to recover the private key directly from this. Also, we found a funny thing that we still cannot really explain, but we were able to find a glitch point that fixes the nonce to 0xFFFFFFFF. So it's even easier. We don't need any kind of lookup table. In that specific spot, we are able to just do the math once and get the private key directly from the device. So it's way more easy, but we still didn't figure out exactly which instruction was glitched and how it was possible to get this specific value without triggering an error.
So as soon as we got the first result, we wanted to disclose this attack to ARM, who managed the library. However, we figured out that the software, which was up to date on ESP32, was not using the latest version of mbedTLS. And we then discovered that, in fact, the read binary function we targeted in our attack was not anymore used in the up-to-date version because of for performance reason, because it's not that efficient to copy value byte per byte. However, we found other way. I mean, we found a way before the copy to attack the signature generation by attacking the CTR-DRBG or HashMac-DRBG algorithm. I won't go too deep into the detail, but the idea is quite similar. If you are able in the code to bypass the update function or to bypass part of the update function with a fault, you will have a nonce which does not depend on secret value, and you will be able to guess this value again and to apply exactly the same attack. So then we contacted ARM with full detail of our attack. We suggested to change the default return value as well because it helps us to mount the attack. So we got a response from ARM saying that they generally do not consider hardware fault attack in their threat model, but they were happy to work with us on this issue. And from this message, we got no more communication from ARM. However, we noticed that in the code, they changed the way they initialize the return status. They created a new status, which is called error corruption detected, which is a nice way of secure coding. And we don't know if it's linked to our disclosure or not, but that was really nice for them. However, it did not correct our vulnerability because in the code, the error status is first used with an initialization function, and then it will be reused again with the function we attack. So the return function will be initialized with success anyway, so our attack is not thwarted by this correction. So to sum up, we have reported the vulnerability to ARM in September last year. ARM acknowledged the vulnerability. They hardened the library with the error status in November. And then finally, Expressive upgraded to mbedTLS 2.16.5, meaning that attacking the read binary function as we have presented shouldn't work now, but the vulnerability still exists because the signature is not protected against fault, and you can attack, as I explained before, the function before this one. What you can do to avoid this problem, the first obvious countermeasure is to use TLS 1.3, because in this version of the protocol, handshakes are encrypted. And if you remember at the beginning of the presentation, we need to have the handshake exchange and we need to have the signature. So if they are encrypted, we are not able to perform our attack. You may want to use RSA for authentication, but there are still other attacks like side channel. So you have to see if it's safe or not to do that. And you may use hardware secure elements, but in this case, it will increase a bit the price of your device. So to sum up, we've presented a full key recovery with a single fault against TLS. And what's important is that this attack is not related to the target. If you have an embedded device which uses mbedTLS and which is vulnerable to glitch, then you are able to apply our attack. It will work. And we've also noticed that as soon as your hardware is vulnerable to glitch, it's really, really difficult to do software hardening. It can be done, but it has to be done really carefully. Otherwise, you won't protect against those kind of attack. So that's all for us. If you have any question, feel free to ask now or in the breakout room.
Sylvain, Nicolas, you must have received questions in your chat.
Yes.
Okay, so hi Nicolas, can you elaborate more on initialization of TLS, i.e. client hello packets? Will there be single cipher suite, unlike browser which offer multiple cipher suites offered to server, or there is a mechanism of certification pinning in IoT clients? So for the initialization, usually the server, in the server hello, it will send all the supported cipher suites. And the client will do exactly the same, and they will agree on one specific encryption scheme. Regarding the certification pinning in IoT clients, this is something that has to be done within the firmware. So usually it has to be done by the developer itself. The one possibility that we see is that you have to compare the hash of the certificate you receive from the server to make sure that it's the same that is within that is hard-coded within the firmware.
Fault attack is possible when you use hardware crypto instead of software library. So yes, it has been demonstrated that it's possible against hardware crypto. However, it's much more difficult, and you may implement more countermeasures in hardware, which will be much more difficult to manage with a fault attack. But it will definitely higher the cost of the attack if you use hardware crypto instead of software, definitely.
Did you investigate single fault attack against RSA cipher suite in the same context? No, we did only try the ECDSA algorithm for now. I don't know, Sylvain, if you did some more tests for this.
Yeah, no, but there is, it's interesting because there is a countermeasure against fault in mbedTLS for RSA. In fact, they will compute the public operation after the signature to verify they have the good message at the end, especially to see if a fault happen in the library. So you will have to attack other part of the algorithm. I don't see other question.
Okay, what we could do is we could continue asking questions if people like to have. Okay, there's one question here.
So how to detect when inject the fault? One possible way is to add more fault detection within the software. So if we take the same target, which is vulnerable to fault attacks, what we could do, for instance, is that if we know that our for loop that copies byte per byte the value, the random value to the MPI structure, what we could do is test the number of loop, the number of occurrence of the for loop, and if it's the correct value, it then the result is okay. If the loop just did let's say 2 rounds instead of 8, then you have a fault and you have to return another kind of error message, error code.
What is the fault success rate on ESP32 with your setup? So if you're injecting fault in synchronized software like a loop, it's quite high. You're able to inject fault in a really high success rate. For this attack against TLS, obviously you have to inject a lot of fault. And I don't remember exactly the time it takes until you have the private key, but nevertheless, you just need one successful fault and then you have the private key and you will be able to authenticate to the cloud. So yeah, it's just waiting the good faults to happen.
So do you know if this attack works on other hardware than the ESP32? As long as it uses mbedTLS in at least in the versions we tested, and this target is vulnerable to glitch, you are able to get exactly the same results.
Looks like, okay, there.
Do you think that 2 faults may be possible? Yeah, like you mean, yeah, to defeat countermeasure. In software, definitely you can make two fault and it will work. Yeah, that's where you want to have hardware protection, but it will increase the cost of the attack and the time until you get the key. Yeah, for the RSA, for example, you can try to first inject a fault in the Chinese reminder theorem part, and then a fault to skip the verification, obviously. But you need to synchronize the first fault and then the second one, so just take more time. But as soon as it is all in software, it should work. Have you tried lasers? Not yet. It was not necessary.
What sort of mitigations could chip manufacturer put into place in hardware to prevent this type of attacks? Honestly, I'm not that into this in this layer. I honestly don't know.
The first obvious one could be glitch detection, but it's difficult to do good glitch detection, especially for system and chip. we didn't try the Chipwhisperer Pro. In fact, we wanted to demonstrate a low-cost attack with a Chipwhisperer, which is like $300, and it worked. But then Chipwhisperer Pro is a bit more expensive, and we would have used more the other tools we have in the lab. But Chipwhisperer Lite is good. It was really good.
Okay, I think we move to the discussion room. Nicolas Sylvain, thank you really very much. Amazing talk.